Hello everyone. In the last session, we discussed about finite difference method, where we looked into kinematic wave models and solved the continuity and momentum equations using the finite difference approximations to the partial differential equations. We learned about implicit and explicit schemes, and we did numerical example at the end. So in this numerical example, you can try a similar problem by taking two reaches. So here your delta x would be equal to 5000 by 2500 meters. Therefore, what you'll get here would be 3 grid lines, and here you'll have 4 grid lines. This will be at x equals to 0, at x equals to 2500, 2.5 kilometers, and at x equals to 5 kilometers. This is your time at 8 a.m., 9 a.m., 10 a.m. and 11 a.m. and you are given this one 70, this one 100, 100 and 100, and let's say you are given the value here and here. Your task would be to find these flows at 2.5 kilometer and at 5 kilometers. So for this you will have to solve for this one like we did here in the example by taking delta x equals to 2500 meters, and then you'll get this one, this one and this one, and then you have to follow similar procedure again by taking delta x equals to 2500 meters, but you'll be solving using these three values here to get this point here. So this solution would be more accurate than that of what we obtained using delta x equals to 5 kilometers. So you can try this and see. Now today we are going to look into chapter 6, which is on method of characteristics. Here, method of characteristics is also a technique of solving your partial differential equations by converting them into ordinary differential equations and then solving for your ODEs. You can use numerical or graphical methods. Method of characteristics is generally used to solve problems related to unsteady flow problems. Now this implies of solving characteristic equations of unsteady flows. The examples of unsteady flow may be in open channel flow or in pipe flow. Now what do you mean by characteristic equations? So these equations are in the form dx by dt equals to v plus minus c. Here, if you have a channel like this and you have water flowing let's look at it from this section here. So what you'll have is, this is your base and this will be your water. Now when your water is flowing, it will create some waves at the surface. We are concerned about these waves here, which may be known as surface waves. Now if you zoom into these waves, you'll find that if this was x and this was time t, then they will follow a sinusoidal type of behavior. This part here is known as crest. This here is known as trough. As you all know, in waves, the distance between two crests is known as wavelength, or the distance between two troughs is also known as wavelength. And this peak here from your x-axis is known as amplitude. Generally, what you assume here is that your depth of the water, which is this part here, stays uniform, and this wave is periodic with time period equals to t, such as in sine wave, your amplitude of the wave is very small as compared to your wavelength. If we consider your depth to be h and your wavelength to be lambda, then based on the ratio of depth by wavelength, you have three types of rivers or waters. The first type is the shallow water. In this case, your depth by wavelength ratio is less than 1/20. In cases of deep water, depth by wavelength ratio is greater than 1/2. And if your ratio lies between these two extremities, these two ratios, then it is known as intermediate water. So you might be wondering what V and C are. This V is the velocity of the flow, whereas this is the celerity of the wave, which is this wave here, and it is given by your wavelength divided by time period, which means that your wave travels at a distance lambda in time period t. This is like your wave velocity. The general equation to calculate celerity is given by where, now in cases of shallow water, which is this one here, your C is given by root under GH. In cases of deep water, your celerity is given by z lambda by 2 pi, and for the intermediate case we have to use this equation here. So this was about the celerity of the wave. Now let's move into our characteristic equation, which is, if you plot this equation, if this was x-axis, this was t-axis, then you may get a curve which may look something like this, where this one represents v plus c and this one represents v minus c. The slope of these curves will be given by tan theta, which will be equal to, if you take a slope here, this is dt, this is dx, this is dx, this is dt, you'll get dt by dx, which will be equal to 1 by v plus minus c. Here these two are your characteristic lines, where this one is known as c plus characteristic line, which has a slope of 1 by v plus c, and this one is c minus characteristic line, which has a slope of 1 by v minus c. To solve using the characteristic lines, you always need initial condition, that is your value of the function at t equals to 0. Therefore you will need your f0, and you also need your boundary conditions. Now let's look at first type of flow, which is gradually varied unsteady flow in open channels. Some of the examples of such kind of flow can be the flood wave. Now here we'll have to look into the continuity equation that we also had a look in the previous chapter. So the continuity equation is dq by dx plus dA by dt equals to 0, where area is given by top width times depth of the water flow. So here in this channel, this is the depth, this is the top width, and this will be your area, and the flow is given by area into velocity, which is volume per second. So if you substitute these values here, you will get, now this is a partial differential equation, so when you open this, what you'll get is now this t here is considered to be constant, therefore again there's one more term, your hydraulic depth d is given by A by t, and your t dy will be equal to dA. So here, if this was small depth dy, then your area here, flow area, will be given by t times dy. Now if you plug in these values here, what you will get would be a given by dt. So dt plus dA given by tdy. So tv dv by dx plus t dy by dt equals to 0. Now you can take your t common and take it to the right side. Since t is greater than 0, this right hand term will be equals to 0. Therefore, what you will get here is d dv by dx plus v dv by dx plus dy by dt equals to 0. Now this is known as the continuity equation for gradually varied unsteady flow in open channels. If you have a rectangular channel which has an infinite width, then what you'll get here will be dq by dx plus dy by dt equals to 0 for uniform flow, where q is the discharge per unit width of the channel. This is our continuity equation C. Now if you look into our second type of equation, which is the momentum equation, in this case, for the gradually varied unsteady flow in the open channel, your momentum equation is given by where dy by dx is the slope of the water surface, y is the depth, x is the section along the channel, v is the velocity of the flow, g is acceleration due to gravity, dv by dx is the change in velocity with respect to distance. This is change in velocity with respect to time. This is the bed slope, and this term here is the friction slope. In the prismatic channels, which means that they have constant dimension along the length, so this one will be b throughout the channel. In such cases, you will have dz by dx equals to bed slope, which is negative s naught. Therefore, the above equation can be written as, if we take alpha equals to 1, now we can see here that this is another equation which is from the momentum equation, and we have our continuity equation, which is this one here, and we'll also have two more equations based on the partial differential equation, where we can write, so this is our third equation and that's our fourth equation. Now if we solve these four equations simultaneously, what you'll obtain at the end will be this equation here. Now in cases of flood, what will happen is that you'll have different surges, and in the surges at a point of discontinuity you'll have two surface slopes at the point of discontinuity which will have no relation to each other. Therefore your dy by dx at that point should be indeterminate. Therefore this can be equal to 0 by 0. Now in this case you can assume your numerator to be 0 and your denominator to be 0. If you take our denominator to be 0, what you'll get is 1 by z. Now you can see here that this is a quadratic equation in dx by dt, which is of form az square plus bz plus c equals to 0. So this is a, this will be our z, this is b, and this is our c. Now the solution to a quadratic equation is, so if you substitute these values there, what you'll get is, now you can see here that this is of the form v plus minus c. Your c is given by root under gd, and for wide channels your c will be given by root under gy. So this is our characteristic equation which we have to solve. Again, if you take the numerator equals to 0 and then use this equation in the numerator, then what you'll get will be, so here this is our first characteristic equation and this is our second characteristic equation. When you plot this, and if you have a grid line, this may be t, this will be t plus delta t, so this will have slope of dx by dt which will be equal to b plus c. This one dx by dt equals to v minus c, or dt by dx equals to 1 by v minus c, and this distance, if we take line here, this distance here will be b plus c into delta t, and this distance here will be v minus c into delta t because of the negative slope. And let's say this is point P, this is point A, and this is point B. So the lines here AP and BP are the characteristic lines. Similarly, when you look into another case which is gradually varied flow in pipes, where you will have your continuity equation, let's represent that by C as dP by dt. In these cases, this value here is generally small and can be neglected, and you will have your momentum equation as dV by dt. In this case also, this term here is generally small and can be neglected. Here, in these two equations, your V will be average velocity over a section. If you are taking a pipe like this, a longer pipe like this, and you are looking into this section here, the velocity can be the average velocity of this section here, and P is the pressure at certain point, and rho is the density. Small c is the celerity of the wave, which is given by where K is the bulk modulus of fluid, D is the diameter of the pipe, which is this diameter here, E is the Young's modulus of the pipe, and T is the thickness of the pipe. Now if you look into the cross section of the pipe, what you'll have here is something like this. This will be your T, thickness, and this will be the diameter of the pipe, and you will have fluid flowing in here. G will be acceleration due to gravity. Sine theta is the slope of the pipe, and F is known as the friction factor. So you will have these variables here. In this case, you will have two unknown variables, which will be the velocity and the pressure. Now we can combine these two equations into one in this form: S equals to m plus certain factor times continuity equation. So this is our momentum equation, this is our continuity equation, and this is just a factor. Now I can plug these in. What you will get will look something like this, and we have two equations which are the partial derivatives of, which implies, and now you can open these two and substitute del V by del T and del P by del T by these equations here. Then what you will end up with will look something like, now you can set this equals to 0 and this term also equals to 0 to simplify the equation. Then what you will get here is dx by dt for this case will be equal to V plus rho c square, and for this case it will be equal to 1 by rho phi plus V, and this equation here will now reduce to, for this to happen, your dx by dt should be equal to this, and your dx by dt should also be equal to this. Now you can equate these two values. Therefore V plus rho c square equals to 1 by, or you'll get your phi equals to plus minus 1 by rho c. I think I missed a phi here. I think here should be phi. So here it will be phi, and you will get your phi like this. So when your phi is equal to 1 by rho c, this condition satisfies. You can back substitute your phi here and then get the characteristic equation. Now your characteristic equation will be dx by dt 1 by rho plus minus 1 by rho c plus v. Now this equals to v plus minus c. So this is our characteristic equation. for the gradually varied unsteady flow. Therefore, we have two equations here as well. So this is our first equation and this is our second equation, and these two equations are known as characteristic equations. And you can again plot our dx by dt like this. So this will be t plus delta t. This is x-axis. Let's say this is m, this is n, and this is o. So this curve is the one with the positive slope. This one is the one with the negative slope. This is delta x, and this is delta t. Now in a case at this point here, you may be given your velocity at m, your pressure at m, you'll have your xm and time, and in this case also you may be given velocity, pressure, your location and your time like this. Now you can see here, you can replace your phi with plus minus 1 by rho c. Now for this case, if you look into the characteristic line with the positive slope, this one, then you can write your momentum equation as, you can see here that we have taken phi equals to plus 1 by rho c. You can rearrange this into, if dx by dt is taken as c, then your c dt will be equal to dx. Now you can substitute these values with dx, then what you will get will be, now what you can do here is you can integrate this equation, which is in terms of x, from here to here, which is at a distance of del x. So you can integrate this from m to o, and then you can write this in finite difference form as, this dv is the difference in velocities at point o and point m. If the velocity at this point is vo and this point is vm, then what you can write here is vo minus vm. Similarly, if you take the characteristic curve with the negative slope here, then what you'll get here will be, now this v here is at point m and this v here is for point n. Now since we have two unknown variables here, which is this one and this one, and two equations here, we can solve these and obtain our unknown variables, which are the velocities and pressures at point O, this point here. So what you can do here is you can represent these two equations in terms of discharge and hydraulic gradient line. For example, if you have a pipe like this, if you take a section of it, and if this was z here and the slope maybe theta, and you have your hydraulic gradient line, HGL, and this is H, and this is our pipe section. Then you can write your pressure in terms of head H minus Z. Therefore, pressure at P naught will be equal to and pressure at PM will be equal to. Now I can subtract these two equations to get our PO minus PM, which is this value here. So PO minus PM will be equal to, now this here, taking this as theta and taking this as delta x, Z0 minus Zm can be written as delta x sine theta. Now I can substitute the value of P naught minus Pm in the above equation. Let's say equation 1 here. Then what you can write here is, and you can cancel these two out, and we can write our velocity in terms of flow divided by area. So you can substitute these values here. Then what you'll get will be, again, we have to find our head at point O. Therefore, HO will be equal to HM. Now, if you consider this as xi and this value here as lambda, then ultimately what you'll get is, and this is for the C plus curve, and for the C minus curve, what you'll get is, therefore you have two equations and you have two unknowns to solve, and you can solve this simultaneously. So here xi equals to C by GA and lambda equals to F by 2D A square. Now we'll look into an example problem for the gradually varied flow in pipes. Let's say you have reservoir here and you have a pipe. Let's say the head here is 150 meters. We can denote this point as A, this point as B. Let the length of this section be equal to 500 meters, and diameter of this pipe equals to 300 meters. Now you may be given your friction factor as 0.02, your celerity speed as 1000 meter per second, and let's say the equation of the hydraulic gradient line at the reservoir follows the sinusoidal wave, that is a sine function as 100 plus 2 sine pi t. For this problem, let's say that this end is closed, which means that the flow at this end equals to 0, and you'll have water here as well. Now the problem here can be to find discharge at this point and your hydraulic gradient line at this point after 2 seconds using only one reach. So in this problem, you are given your head at A as a function of time since you are given your celerity speed. As we all know that we assume our current number to be equals to 1 and our celerity speed is given by delta x by delta t, which implies our delta t equals to delta x, which is 500 for this case, divided by 1000. So this equals to 0.5 seconds. So we have to take an interval of time as 0.5 seconds and our spatial step as 500 meters. Now for the C plus curve, we can look at this equation here, and for C minus curve we can look at this equation here and substitute the values. So you can write HOB, which you have to find out, will be equal to HA minus, which is equation 1, and HOA, and for C minus, HOA equals to HB, where Xi equals to C by GA. This will be equal to 1000 by 9.81 times area. So your area will be given by pi d square by 4, which is the area of the pipe. This equals to pi into, which will be equal to 0.071 meter square, meter per second, meter square, meter per second square. Now what you'll get, your Xi as 1435.73, and your lambda will be equal to delta x as 500 Now here you can substitute this value back into these equations, and you can substitute the value of lambda back into these equations here. So you'll have two equations which you have to solve simultaneously. I'll do this in the Excel sheet and upload the Excel sheet with this video so you can have a look at it. So this is our problem here. So we are given friction factor 0.02, celerity speed 1000, diameter of the pipe 300, and our reach delta x as 500 meters, our head at A equals to 100 meters. Now we have to find after 2 seconds discharge at A equals to what and head at B equals to what. Now let's find out our step. So delta T will be equal to or delta X divided by C. So this is our delta T in seconds. Let's calculate our area here. Area will be equal to, now our xi will be equal to C by GA. G is 9.81 into area A. So this is our xi. And now to find our lambda, which will be equal to F into delta X divided by 2 into G, which is 9.81 into D in meters times area square. So we got our lambda as well. Now we have to form a table from these two equations. What you can do, you can find HOB and QOA. Your HOB will be given by this equation directly, but for your QOA you have to do some manipulation here and obtain your QOA. So what will happen is, so here T equals to 0, and you can see here that our delta T is 0.5, so we have to add 0.5 for our next step. So we have to keep adding that till we reach to 2 seconds. So this is our required time as 2 seconds. So HOA, the head, here is 100 initially, QA is 0, HA equals to 100, HB equals to 100 in the initial condition. Therefore your QOA will be given by this equation here. So this equals to HOA, this one, minus HB plus lambda into QB. QB is 0 all the time, so it will be 0 plus xi QB, which is xi into 0, because this pipe here is closed. Therefore your QB is always 0, and this all divided by xi. So this is our QOA. Now once you have your QOA, you can get your HOB. So your HOB be equal to HA minus QOB, which is 0, minus QA, which is this one, minus lambda, which is here, QA is this one, Also QA is this one times QA, absolute of QA. So this is our head at B. So for this case, your HB will be equal to your previous HOB here. So your head is given by this equation here, your head at A, which is 100 plus 2 sine pi t. So this one here, this will be equal to 100 plus 2 times sine pi into time t. So this will be your head variation. So when you plot this, you can see that this curve is, so here you can find your flow at A, which is this one, and your head at B. For the first case here, our head at A is given by this equation here, which is 100 plus 2 sine pi t. So you have to write it here, and you'll have your t as your variable. So these all will be based on your sinusoidal equation as plotted here. And then your QA for the first case equals to 0, head at A equals to 100, head at B can be assumed to be 100 as well. So this flow QOA is given by this equation here, where your QB is always 0 because this is closed, so there will be no flow outside. So this equation will reduce to HOA minus HB by xi, which you write it here. And then for HOB, you'll have your HA minus xi times QOB, which is 0, minus QA, which is this one, minus lambda times QA into QA, which is this one. This is the absolute value, so you write it here as absolute, and then you can see your values. Now you can just drag it down like this, and then you'll have your solution. Now this head here will be equal to your previous head, which is this one, and your QA will be equal to your previous QA. So this is how you obtain your solution, which was to find your flow at A after 2 seconds and head at B after 2 seconds. This should have been minus, so you'll get minus here. So this is it for today. In our next session, we'll look into the final chapter, which is on simulation of groundwater flow, where we'll discuss about how to solve partial differential equations related to underground flow and seepage under the dam using one-dimensional implicit scheme. See you next time.